Hello, welcome to another lesson in Algebra 1. Today we're covering section 2.1, use integers and rational numbers. All right, so for a warm-up, it says complete the statement using, remember, less than, greater than, or equal to. Okay? So we have 1.3 and 1.03, and sometimes I'll tell people to make sure you have the same number of decimal places after the decimal. It's easier to see. So this is like $1.30 or $1.03. So $1.30 is definitely bigger. Okay. Number two, if I'm doing this, and there's a couple tricks here. One, you can get the common denominators. Okay. So you can say they're both 72, and then you can change their tops. 9 times 5 will give me 45 here, and 8 times 6 will give me 48. And then we can see that the 48 one is bigger, so 6/9 is bigger than 5/8. You can also just turn them both into decimals. So 5/8 is 0.625, and 6/9 is 0.6 with a bar, so 666. So the 0.6 with a bar is definitely bigger than 0.625, because you could just say like this, 0.666, and then an extra 6 with a bar, and you can see that 666 is bigger than 625. Okay. The last trick is you can just take the top number at one end and the bottom number of the other and multiply them together for 45 over here. 6 times 8 would give you 48 up here. And what I'm doing one more time is taking the top of this one, timesing by the bottom of that one, and write it on the same side as the top. Okay. And then the top of this one times the bottom of that one, and write it on the same side as the top. And whichever is bigger is the one that's really bigger. So in this case, you end up with the same tops as we do when we get common denominators. So the 6/9 is bigger. Okay, so some tricks on how to order fractions. All right, so we have sets of numbers. We have the whole numbers first off. The whole numbers are the ones you learned in kindergarten. They start with 0, and then you count up 1, 2, 3, 4, 5, 6, 7. Notice there's no decimal parts and no fraction parts. That's what makes them whole numbers. Okay. Then we have the integers. The integers are the whole numbers and their opposites. So it goes on forever in two directions. Still no fractions or decimal parts. Then we have the positive integers, which are, of course, 1, 2, 3, 4. Notice we leave out 0. 0 is not a positive number. And we have the negative integers, -1, -2, -3, -4, so forth. Okay. So in this set, notice there are no decimals or fractions yet. Everything is going to have a perfect, end up perfect with a decimal point of 0.0. Okay. All right, so graph -3 and -4 on the number line and tell which is greater. So here is -3. Here is -4. So obviously -3 is greater than -4. Anything to the right is always bigger. You can also think of this as I owe $3 or I owe $4. So if you graph them on the number line, the ones on the right are always bigger than the ones on the left. 0 is bigger than -5 because it's to the right of -5. Okay. All right, now time for some fraction and decimal stuff. That's called rational numbers. Rational numbers are any numbers that can be written in the form of a over b, where a and b are both integers, and b is not 0. So for instance, 5 is a rational number, because we can write it as 5 over 1. Okay? Or 1/3 is a rational number. Notice a and b, so the a is 5 in this case, and the b is 1 in this case. They're both integers, okay? And for 1/3 or -1/3, the a and b are both integers, okay? All right, so which of the following are rational numbers? So let's see if we can write them in such a form of a over b where a and b are integers. So 1 over 1, we could rewrite this by. So he's a rational number. This is 1 over 2. He's already got an integer on the top and an integer on the bottom, so he's a rational number. This one is -3 on the top and 4 on the bottom, or 3 on the top and -4 on the bottom. It doesn't matter. So he's a rational number. 0.25 is the same as 1/4. Now we have integers on the top and bottom. And -0.3 with a bar, or 0.3 with a bar, is 1/3. So we can write that repeating decimal. All repeating decimals are actually rational numbers. So this guy. So which of the following are rational numbers? All are rational numbers. So there are things that aren't rational numbers. They're called the irrational numbers. A couple famous ones, pi. Pi can only be approximated. It has a decimal value that goes on forever and never repeats. So all we can do is an approximate for it. That's the difference between rational numbers and irrational numbers. And we'll see irrational numbers later in the chapter. Okay? All right. Tell whether each of the following is a whole number, an integer, or a rational number. So 7 is a whole number. Check. 7 is an integer. All whole numbers are integers. And 7 is also a rational number because we can write it as 7 over 1. 0 is a whole number. Check. That's the first whole number we come to. It's the middle integer. Check. And all integers and whole numbers are also rationals because you could write this as 0 over 1 or 0 over 2 or 0 over 3. There's lots of ways to write it. Okay, so check. Whole number here? No. Integer? No. We have a decimal part. But we could write this as negative 5 over 4, improper fraction, so therefore it's definitely a rational number. All right, 0.3 is neither a whole number nor an integer because it has a decimal part, but it is a rational number. We could write it as 3 over 10. Okay. All right, list the numbers in order from least to greatest and then tell whether each number in the list is a whole number, an integer, or a rational number. So first off, the smallest numbers are going to be negative. This one, negative 3/4, is really like negative 0.75, and that's definitely bigger than negative 2.1. I'd rather owe 75 cents than $2.10. So negative 2.1 comes first, then negative 3/4. Notice I'm listing the way they're written up here. I'm not going to put my decimal equivalent, okay? Same thing on the quiz. Please use what's listed. Don't use a different format, okay? All right, and then 50 cents is smaller than $4.50. Okay? All right, so these are the numbers in order. None of them are whole numbers. None of them are integers. They all have decimal parts, but they are all rational numbers. Okay? Negative 2.1 could be written as negative 21 over 10. 3/4, we've already seen that, so it's already written as a rational number. 0.5 is 1/2, and 4.5 is 9 over 2. Okay? By the way, your calculator can do this. If you type in 4.5, and then you can hit math and then enter twice. That's how you turn it into a fraction on the graphing calculator in class. Okay? And this will come back as 9 over 2. Opposite numbers. Opposite numbers are numbers that are the same distance from 0 on the number line, but are on the opposite sides of 0. For instance, 4 and negative 4 are opposite numbers. Because here is 0, 1, 2, 3, 4. 1, 2, 3, negative 4. So these are both 4 steps from 0. Okay? So they are the same distance. 1, 2, 3, 4. Or on this side, we could count 1, 2, 3, 4. So in both cases, they're the same distance. So 4 and negative 4 are opposites. Okay? Find the opposite of each number. Well, 5 steps to the left of 0 would be negative 5. So this guy's its opposite. Please don't put equals between these because 5 and negative 5 are definitely not equal to each other. The opposite of negative 2 is positive 2. So please don't put equals 2 there. All right, if A is negative 2.5, then what is the opposite of A? So to get the opposite of a number, we just change its sign. So, or we could think of it as timesing by as negative 1. So the opposite of this guy would be negative A, make it the opposite. And then over here, that's going to make negative of negative 2.5. So two negatives multiplied together, which is what's happening here, will turn into a positive. Okay, so negative of a negative. It is negative, flip it back around to positive. Okay. All right, last page here. Absolute value. Absolute value of a number A is the distance between A and 0 on the number line. So the symbols, this is the symbols for absolute value, and it's read as the absolute value of A, the absolute value of whatever is inside the bars. Okay, so for instance, like the absolute value of negative 2. All right, so on a number line, there's negative 1, there's negative 2. To get from negative 2 to 0, we'd have to walk 2 steps. So the absolute value of negative 2 is 2. Okay? or the absolute value of a positive number, still have to walk 3 steps to get back. So what it does is it takes negative numbers and makes them positive and leaves positive numbers alone. Okay? Absolute value is really a grouping symbol, so you must work out what's inside the bars to a single number before you do the absolute value part. Okay? All right, so part A here says what's the absolute value of 5? That is 5 steps from 0 on the number line. And the absolute value of negative 2.5, that's 2.5 steps from 0 on the number line. Okay? A conditional statement. A conditional statement has a hypothesis and a conclusion. You see these in science classes. Okay? It's an if-then statement. Okay? So an if-then statement is a form of a conditional statement, so it's one way to write a conditional statement. The if part is the hypothesis. Okay, so the hypothesis goes with if. And the then part is the conclusion. So the conclusion goes with then. So in mathematics, an if-then statement can be either true or false. If the if-then statement is true is when the condition of the hypothesis are true, the conclusion is also always true. So if I pick any condition that makes the hypothesis true, it has to make the conclusion true. If the conditional statement is false, if the counterexample can be found such that I pick some hypothesis that's true, but the conclusion is false. And this will be the trickiest part of the test for many of you. Okay? So an example of a true conditional statement. If it is raining, then there are some clouds in the sky. So have you ever been outside on a day when it's raining and you didn't look up and see at least some clouds, probably right directly above you, or maybe off to the side a little bit and the wind was blowing the rain into you? So this, no matter what, okay, so the hypothesis here is this part. The conclusion is this. So if it is raining as a hypothesis, so we think of all possible days it's been raining on, water falling out of the sky, not put by the sprinklers. So if it is raining, then there are some clouds in the sky. And that is a true conditional statement. But if I flip it around and I try to make it if it's not raining as the hypothesis, then there are no clouds in the sky as the conclusion. So can we think of any, so this was a true one, remember? Can we think of any example where we've been outside and it hasn't been raining, but it's cloudy? And we all live in Germany, so we know that that's possible. We go outside, it's not raining, but there are clouds up above us. Okay, there are always going to be some clouds in the sky for most days in Germany. Okay, so this would be a false because I caught up on one counterexample. On Friday, September 23rd, 1965, Joe went outside and he saw clouds, but it wasn't raining. Okay, so he went outside, it wasn't raining, and he saw clouds. All right, so tell whether each conditional statement is true or false. And these are the ones you're going to see on the quizzes and tests. They're going to be talking about the sets of numbers. And you'll see these in higher math when you get to college too. So if a number is a rational number, then the number is positive. So rational numbers. So rational numbers are any numbers that we know of that, except for decimals, that go on forever and never repeat. So can we think of any counterexample of a rational number that's not positive? Yeah. I can. So this is going to be a false statement. And all I need to say it's false is to have one counterexample. So my counterexample is going to be 0.5, negative 0.5. So negative 0.5 is a rational number. I can write it like this. That's the ratio of two integers, or write it as a fraction. Okay? Then, is it a positive number? No. So here's my counterexample, negative 0.5. Right? So if the absolute value of a number is positive, then the number was positive. So is this a true or false conditional statement? So remember, for it to be true, every number we think about that has a positive absolute value should then also be positive. Okay? So I think this one's false. Okay? The absolute value of a number is positive. So here's my counterexample. I'm going to go with the number 10, negative 10. So the absolute value of negative 10 is 10. Then the number itself is positive. No. So here's my counterexample. And it's going to be negative 10. It has an absolute value that is positive. That's this part. However, the number itself is negative 10, which is not positive. So I have a counterexample. I thought of something that made the hypothesis true and the conclusion be false. And that's what we want to happen. If we can think of anything that makes the hypothesis be true and the conclusion false, then we know the whole thing is a false statement. Okay? So here's my false statement with a counterexample of negative 1/2 or negative 0.5. And here is my false statement with a counterexample of negative 10. Okay? All right. I will see you in class next time. And hopefully we have Khan Academy already sent to you. Some of you were able to do it in class, hopefully after the test, depending upon whether you were able to get on a computer or not. And the rest of you need to look at your email invite. Make sure that you join our Khan Academy class and take the pretest. I will count this as a grade. If you are not in my Khan Academy class, when I look on next time I see you in class, then you will get a 0 for that grade. Okay? So if you're having some trouble with that, come back and see me in advisory and make sure that you get it done, or come and see me after school. All right, see you in class next time.